Hello everyone. So today we'll be solving another dynamic programming question called longest common subsequence. The question reads as given two strings text1 and text2, return the length of their longest common subsequence. If there is no common subsequence, return 0. A subsequence of a string is a new string generated from the original string with some characters, can be none, deleted without changing the relative order of the remaining characters. Okay. For example, ACE is a subsequence of ABCDE. A common subsequence of two strings is a subsequence that is common to both the strings. Okay. Now let's see what it says on the whiteboard. So it's saying that we have like a string called T1 that is A, B, C, D, E. Another string right here, T1 equals to A, B, C, D, and E. Another string T2 equals to, let it be like A, C, E. Then the common substring here is A, C, E. And as the order is same, and we can delete like D and B, B and D from the top one, and we'll get the common sequence in both the strings. That's what it says. So one thing, the string should be present in both, right? Condition 1, it should be in a sequence from left to right in both, and then we have to return the longest one. For example, A is the substring, AC is the substring, and ACE is the longest we can get out of this these two strings. So the longest length is 3. So now let's try to draw a decision tree and see how it looks. So for in first case, if you take T1 and T2, if you compare, right, A with A, right, the first character of both the strings. So let's do that, where I equal to 0 and j equal to 0, means let it be I, let it be j, pointer, right? A and A, the both character here are matching, right? When both characters are matching, then we have to return the previously calculated substring length plus 1, that is now 1. So when both the character are matching at I and j, we just have to take it out and we have increment to I plus 1 and j plus 1, right? So now I became 1 and j become 1. So this became B and C. Now in this particular case, we have to compare B with C and E. So it's C, then again we have to compare B with E. So we're going to keeping the pointer I constant and moving this pointer of j to compare with every character. Now here E is reached the end of the string T2, so we don't find a substring, so it will return 0. But here in this case, we're going to keep the C constant, C is not equal to B. We're going to move the pointer across the T1. We're going to move the I1, right, I pointer. So this will become CD. Again it will become CD, then C, this will become CC now here, CC. So again it will become same. So we get 1 plus 1, 1 plus 1, this is equal to 2, and we're going to move the pointer to E here to D, right? Now it will become DE And now in this particular case, again we keep the D and move E. So E is end, so this is return as 0, but now we're going to keep this E constant and move with D, ED, then again we get EE. So if you make it this constant and move this pointer, we will get ED, ED, EE. So again we're going to get plus 1 here, so total will become 3. So that is the you get. I hope you got the idea over here. So what you're doing is, first we comparing both characters I and j. If it's same, we got a match, right? If not, we have to compare each character of one string with every character of other string. For example, we took A, we take it out, then we will keep B, then we're going to compare B with C and E. At the same time, we're going to keep C and C, we're going to compare with B, C, D, E in both way. Now, when we compare this with this, and the T1 character with T2 and T2 character with T1, we will get some set of substrings, and at that time we have to return the maximum of both. So first we're going to do one thing. We're going to solve this using recursion, and then we will see how to do it using dynamic programming. So let's try to implement this using recursion first. So let's create another function here called LCS, and that will take our T1, T2, then I and j. In this particular case, now first we will be comparing the condition where both the character of the string are equal, right? First we're going to do the break case where if I and j reached any of the end of the strings, we have to return 0. So let's write that cutoff condition, like if I greater than equals to T1 dot length, or j greater than equals to T2 dot length, return 0. Okay, so this is this covered our end case when we reached the end of one string, and then we're going to cover the equal condition, that is if T1 dot char character at I equals to T2 dot character at j. If this happens, then we have to return 1 plus previously calculated length, and that will be like we will add 1 and 1 to previously calculated length, plus we have to increment the I and j pointer by 1. So we have to move the pointer in both the strings. So let's do that. LCS T1, T2, now I plus 1 and j plus 1. So this will move the pointer by 2 in both the string. Now the condition where we're going to keep one character of T1 constant and move the pointer across the T2, right? So let T1 compare with T2, right? We'll T1 pointer Now let's T1 compare. So we are keeping T1 constant and moving across the T2. So we are comparing T1 with the T2. So this will return, this will become LCS T1 T2, and then we are keeping the T1 constant here, so it will become I remain constant, and we're moving the pointer through T2, that is J plus 1. And we do the reverse now. We will keep it T2 compare, where we're gonna keep, we're gonna keep the T2 constant and move the pointer across T1. So we're going to I plus 1 and keep the J constant. And when you compare one character with other in both the string, we have to return the max. Return math.max of T1 compare and T2 compare. Now let's call it and return LCS. We're going to pass T1 and T2, and the initial indexes will be 0 and 0. So this should solve our problem. So let's go and run the test cases. Okay, this is the recursion one for the test cases, and let's run those. So it passed. So the recursive tests are passed. So now then, let's derive our dynamic programming from this one, because in this tree, you see, because we are comparing T1 with T2 and T2 with T1, we find that the indexes I and j, we can come across I and j that were calculated before. So definitely we can implement dynamic programming to use the previously calculated values. Right here also we can use memoization to do that, to increase the performance a little bit. So let's try to do that here. Okay, so if you use memoization and improve it, we're going to create a map here. Let map equals to new map. Okay, and in this particular case we're going to map dot set I plus, I have to make a star or something, and then plus j, then 0. I don't want to make I plus j because that will give us wrong value. It will add this up and we will get wrong value. So I'm adding a string so that this particular ij combination will stay unique in our map. Same way we're gonna do in our one condition as well. Character I and character j. I think we don't have to do it because anyway we're gonna increase. Once we match the same thing, we're not gonna get the same ij again, so we don't need to do it here. No, we need it. Let's do it. So here I think we can do map.set. Let's get this in a variable called result. Temp. Let's do this. You can put temp here, and we're going to return temp. And at the top of this LCS, we're going to check if the values exist. If map.heads this particular I_j, then we're gonna get it from the map. Return map.get. This should do our trick. So we're gonna memorize these stuffs with ij combination. If it's 0 or if it's ij, we get equals to, and we get a value. And then when it comes the same ij again, if it's present in the map, we just will return that. So let's see if it passes. Ooh. Oh, sorry. Copy paste issue. Should be get. Boom. So we are good. Now let's try to implement dynamic programming from the same decision tree we made for our recursive problem. So let's go to whiteboard again. So in this particular case, let's put this in a matrix of m cross n. So we're gonna do right A, B, C, D, E, C, D, E, and here we're gonna have A, C, and E. So we're gonna start with 0 because we're comparing nothing with nothing. So the longest substring length will be 0 at the initial length. And now at first time A becomes A equals to A. So at that time we know that when A equals to A, we have to add 1 to previously calculated substring length. Here in this position, previously calculated substring length is 0, so you're going to add 1 to get the current value, that is 1. Same way, now when we are here, so we are just our second T2, our second substring is only A, not ACE. Now we are trying to see if A has any common substring in B. So we get maximum length A. So when you compare B, nothing is not the same. So our substring length will remain the same that we calculated before. So it will remain 1. Okay, 1 or same way. Here we are calculating B. We are comparing A with A. We are now comparing AB with A. So there as well, you know, here the length becomes 0, where B, the previous when you comparing AB with A, and when the pointer is B, and we are comparing with A, the match is not the same. So we will be copying the previous existing value, right, from that is 0. So so what happened here is, So to derive it, and in our recursive, we are moving one pointer through the T2, one pointer to T1, and then used to get the maximum. So here is the same. So to derive this one, when it doesn't match, we have to go to the pointer from T1, and what is the result for pointer T2? These two, maximum of these two equals to 1. That's how you're going to derive. So it's 1. So previously calculated length. If it's not the same, then see if they move 2 pointers and what is the maximum. We are doing it here. Same goes to here, maximum of these two, but here C equals to C, so we get a match. So previously calculated length, that is 1, and will be add 1 to that, that is 2. Here DC is not the same. So what if we move pointer across T1, what is the value we're going to get? Like 1. If you move the pointer across T2, what is the value you're going to get? 2. So what will be the value here? Maximum of 1 and 2, that is 2. Same way, and here is the same maximum of these 2, maximum of these 2 equal to 2, and here again E equal to C. So previously calculated value 2, now plus 1 equals to 3. So our maximum substring equals to 3. The same concept that we implemented in our tree, we're going to make a dynamic programming and do the matrix. So once you derive that, you see how you're going to calculate here. So every time our T1I equals to T2J, we are referring the value that is there diagonally and making it plus 1. So T like I minus 1, J minus 1, plus 1, right, in that position. But if that is not matching, so we have to find the maximum of two values that we get moving the pointer across T1 and moving the pointer across the T2, and that will become like ij position equal to I minus 1j max of, and I minus 1j and I j minus 1. So position, top position and left position, to get this particular value for the current position. And that's that. At the end, we just have to return the end value of the matrix. So now let's go ahead and implement this logic using JavaScript. So first we're going to create a DP array, like let DP equals to array of T1.len length plus 1, so that we're going to initiate the first row and first column with zeros, right? Then we're going to fill it with, we're going to create the columns, array of T2 dot length plus 1, and we're going to fill everything with 0. So our whole matrix, now we created m plus 1 and n plus 1 cross n plus 1 matrix, and we initiated every field in the matrix with zeros. Now we have to loop through this DP. Now for, we're going to do I, now DP dot length I plus plus, perfect. Now we don't have to do this. Same way, why? Length, okay. Now same way for J, then you're going to do DP of 0 dot length, so that will give us the columns. So now we have to keep the first row and first column zeros intact, right? That is the initial value. So we need to start this with I equal to 1 and j equals to 1. Now we're going to write our conditions. So first condition is when t1 first in the ith of t1 equals to ith character of t2. So in this case, because our indexes of the string starts from 0, so when we do I and j, we have to compare I minus 1th index, right? So if t1 dot char at I minus 1 to t2 dot character at j minus 1, then we have to populate the current value with the diagonal value of the dp. So dp I j equals to dp I minus 1 j minus 1. Okay, now we have to handle where the characters are not same. So we have to find the we have to keep t1 constant and increment t2. We keep t2 constant, increment t1 and find the max. In that case, it will become like else dp of I and j equals to math dot max of dp I minus 1 j and dp I j minus 1. So this is all. We derived our matrix. So our result should be now at the end element of the matrix. So we're going to return our result. Now return dp of no, we don't have to calculate, right? You can just pop it up, pop, and then pop. We're going to pop twice, and this should return our value. Now let's go and let's run the test cases. This is our dp function. Let's run it. Something is wrong. Length plus 1, length plus 1, field 0, perfect. I1, J1, dp dot length plus I plus plus, perfect. Character at t2 j minus 1, dp is dp I minus 1, j minus 1, and then else dpij dpi minus 1j dpi j minus 1 return dp. It's correct. Is there any other condition that we missed? Ooh, you know what, we forgot. So it is not on the diagonal. We have to 1 plus the diagonal value, right? Because we are increasing the previously calculated value and plus 1. So this is the mistake. So now let's run the test cases again. Boom, and we are good. It's passed. So that's the solution for the longest common subsequence problem, and we solved it in both way, using recursion and using dynamic programming. So thank you for watching.